The N-path filter is a bandpass filter made of low-pass filters, resistor, capacitor. Although the initial research for this filter started back in 1947s, they were impractical until recent years due to poor matching capacitors. But with the CMOS technology, this filter's implementation is practical for modern receiver design. The main benefit of this filter is that it has a high quality factor. The quality factor determines the bandwidth of the bandpass filter. So higher the quality factor, the narrower is the bandpass. Another advantage is that the bandpass frequency is also tunable for these filters. So the way the circuit works is that it uses switches that are driven by non-overlapping clocks. So I'm modeling my switch by a transmission gate here, and these are my clocks here. These clocks are non-overlapping to avoid charge sharing between capacitors. The duty cycle for all the clocks are same, and when the input frequency matches the frequency of the clock, you let the input through the circuit, so you let it pass, pretty much. So right now I have my input frequency at 1K, and all of my clocks are at 1 kilohertz frequency as well. So when I run this circuit, this is the waveform that I get. As you can see in the beginning, the output does not look that great. Like, it's just very not good. But as the capacitors charge and as time goes by, the capacitors start making a very staircase approximation of a sine wave, which means you can actually get a sine wave out of this waveform. However, if I were to change the input frequency to say something like 12 kilohertz that does not match the clock frequency, then when I run this simulation, this is the output I get. Sorry, it's taking a minute. Okay, here we go. So right now my input frequency does not match the clock frequency, and as you can see, my output is like almost a DC. Like, it's a very, very small waveform, and it does not grow. I mean, it grows, but overall, compared to the input, it's very small. It's in the millivolts range. Since, like I mentioned before, this filter is for RF, it has an RF implementation, I figured why not try it at a higher frequency. However, this was what my output looked like when I tried it at a higher frequency, 1 gigahertz. As you can see, this output waveform is not exactly a staircase approximation of the input frequency or the input waveform. And I also noticed while looking at the voltage across each capacitor is that there was slight leakage and maybe something to do with feed through. I'm not exactly sure what's happening, but that's something I need to work on if I want to actually use this filter for what it's designed to. But at lower frequencies like 1 kilohertz or whatever you set, like between 1 to 10K, like whatever input clock frequencies you set to, it works as expected. And yeah, that's the overall circuit. I use transmission gates. So basically, use transmission gates, the capacitors charge, each switch, this switch is open. There's no overlapping between the switches, so only one path is active at a time. So 8 path means that my clock is divided into 360 divided by 8 degree out of phase, and each capacitor is charged, and over time they give a staircase approximation of the input sine wave. Thank you.